Hello, my name is Grace Lee, and this is Lab 5, the Human Rocket. So, as a brief introduction, the goal of this lab is to track the drag force, aka air resistance, of the guy jumping out of the plane. And some fundamental principles at play here are obviously the drag force, along with the position and velocity update formulas. And some fundamental models that will be used in this in this lab is GlowScript. And just as a preview of the results, the result is modeled after the drag force model. No surprise there. Some important equations this should be reviewed. The drag force is equal to constant b times velocity squared, along with the position and velocity update formulas. So some logistics of the lab. The system is uh, Felix Baumgartner. That was the guy who I was mentioning earlier, and RIP. And the surroundings are the Earth, and this lab is purely simulation. So some initial conditions in this lab are that the mass is 66.1 kilograms, and this specific mass was chosen because, well, his mass isn't readily available, so that his height is 5'7". So the average weight for a 5'7" man is 66.1 kilograms. And the initial position and the initial velocity are both initialized to be 0, and t equals 0, and delta is that number. G is initialized here, and j hat is also initialized here, and the b for for the purposes of this lab is equal to 50. So for the actual experiment itself, um, first, F-grab and F-drag are calculated, and then F-net is calculated from the sum of those. And then, using that, the velocity and position update formulas are used here using F-net along with all other constants said before. And then T is updated, and then, yeah, the code runs. And at the end, it says finished. And here's the result of all that code. So the cyan arrow represents the drag force, while the orange arrow represents the force of gravity. And as you can see here, the drag force, like it would be without the drag constant, so b equals 0, the position time graph would be linear. However, if you can see here, this is not the case. And and the velocity and time graph is not completely linear either, which also checks out with the drag force. So, discussing this lab, this model clearly shows that air resistance can be modeled through the drag force equation. So, in the model here, uh, the guy is falling down, which he experiences air resistance, aka drag force. And along with this equation, the position and velocity update formulas help as well. And some possible errors in this lab is the possibility of incorrect coding, as the code, while yielding the same result or the correct results, do not is not implemented correctly. So there are two what if questions for this lab, and the first one is, what if the drag force constant b was increased? And the second question is, what if the initial velocity was -1 instead of 0? So let's start with the first question, what if the drag force constant b was increased? Well, when put through the code, oh, this is with b equals 100, so this is b doubled from the initial experiment. You can see that the drag force arrow here is much bigger than the initial drag force arrow. And you can see that the velocity is much more curved than the initial. All right, moving on to the second question. What if the initial velocity was initialized to -1 instead of 0? Well, as you can see here, there's practically no difference between this and the original model. So there, according to this model, there's no difference. The initialization of -1 instead of 0 has no impact. All right, that's the end. Thank you.